Hello, my name is Navinda Nakhalawong and my colleague is Namlin Rueang-ngam. Today, we are going to present our project in the title An IoT-based vital sign monitoring for at-risk patients.
In an epidemic situation, monitoring at-risk patients is not an easy task, since the number of health professionals may not be sufficient for patients, such as field hospital or primary health care in remote areas. A survey in Thailand from the beginning of the COVID-19 epidemic to April 13, 2020, reported that the number of medical staff has been contracted as 4% of total number of patients.
Moreover, in an emergency patient tracking process, such as in an ambulance or in rescue vehicles, vital signals are often discontinuously informed to the hospital.
The objective of our research is to create a vital sign monitoring device which can detect the heart rate, percent of oxygen saturation, temperature, and respiratory rate with acceptable accuracy. The device also has an ability to send such vital signs to an IoT server for real-time monitoring.
Now let's move on to the scope of our research. Our scope is divided into two parts, which are device parameters and data transmission. We aim to make the device be able to detect at least four parameters, which are heart rate from 33 to 150 beats per minute, pulse oxygen saturation from 96 to 100%, respiratory rate from 0 to 45 beats per minute, and temperature from 29 to 38 Celsius. The range of these parameters are designed based on a pilot testing with healthy subjects, so such range can be adjusted later as a future work.
Next is the scope of data transmission. We aim to create a device with an ability to send vital signs data through Wi-Fi and connect with an IoT server. A web and application-based monitoring are also developed to monitor such vital signs. The rate of data transmission can also be adjusted from 2 to 6 seconds per bunch of data for heart rate, SpO2, temperature, while the breathing rate was constantly set to 1 minute. We move on to our background. First, I'll talk about photoplethysmography or PPG signal. PPG is an optical method used to detect blood volume changes in the microvascular beds of tissue. APPG is obtained by exposing light with red and IR wavelengths through skin, then detecting the absorbed or reflected light with photodetector. The frequency bandwidth of PPG signal is between 0.5 to 4 Hz. SpO2 is an estimate of oxygen saturation within the peripheral capillary. It is the percentage of oxygenated hemoglobin compared to the total amount of hemoglobin in the blood. SpO2 is defined by the ratio between the amount of absorbed light of oxygenated to the oxygenated hemoglobin. In practice, the estimation of the SpO2 can be calculated from the PPG signals by taking the ratio between DC amplitude and the DC plus AC amplitudes. Next, I will talk about the perfusion index or PI. The PI is an indicator of PPG accuracy used for checking whether a subject has weak pulsatile or not. The perfusion index can be calculated from the ratio of the moving blood flow, or an AC component, to a non-moving tissue, or DC component. PI values can range from 0.02 to 20%, representing low to high quality of PPG signals. So this slide shows the perfusion index equation here, which can be determined by the ratio between the AC and DC component. Now I will talk about the heart rate. Heart rate is generally calculated from the time difference between R to R peak of the ECG signals. When it comes to the PPG signals, heart rate is calculated from the peak of AC components, whereby the blood vessel contracts and expands according to the heart rhythm. In practice, we can take derivative of the PPG to locate the sharp peaks before calculating heart rate. Pulse rate variability is a series of change in instant periods of heartbeat. We take the time interval between consecutive peaks of the PPG signals. As you can see in this slide, DI is any time distance between peak to peak. So PRVI is equal to DI plus 1 minus DI.
Respiration rate is the number of breathing per minute. One breathing is counted from consecutive one inhale and one exhale. In physiological principle, the phenomenon called respiratory sinus arrhythmia, or RSA in humans, is a modulation mechanism between breathing rhythm and cardiac acceleration. When inhalation occurs, it causes the high heart rate, while exhalation causes the low heart rate. The RSA corresponds to pulse rate variability, or PRV, since the construction of the PRV depends on the frequency of heart rates.
Now I will talk about the body temperature. Since an abnormal body temperature can be used as a biomarker for detecting abnormality, the normal body temperature is between 36.1 to 37.2 degrees Celsius. Accurate temperature is normally measured by the contactable digital thermometer. The non-contact digital thermometer can be imprecise due to the environmental factor.
Let's move on to the Internet of Things, or IoT. IoT is a specific Internet system provided for electronic devices which can connect through wireless communication. The IoT uses a protocol to communicate between a machine to machine, so-called Message Queuing Telemetry Transport, or MQTT. The MQTT has two types of device. First is a client or an IoT device. Second is a broker or an IoT server. Two types of message used in the MQTT are publish and subscribe. The publish is to send data from a sensor device to a target machine, such as a computer or smartphone, to the IoT server. The subscribe is a message which handshake data to confirm an availability of a target machine.
The IoT platform we selected is the NetPi 2015, which is made by NSDTA Thailand. The NetPi 2015 is a cloud platform that can facilitate communication among IoT devices. The NetPi server allows devices to show their data or any content on NetPi dashboard for free. NetPi platform service consists of cloud storage, a data management, visualization system, interfacing library for various hardware.
Now, let's move on our method. This slide shows the overall process of our project. First, we set objectives and study literature. Next, we design both hardware and software, along with implementing a prototype and developing an algorithm. Then, we tested the accuracy of our prototype. After that, we add the IoT function to the prototype for IoT data transmission. We then configured parameters at the NetPi server and designed a user interface. Lastly, we tested accuracy of different data transmission rates.
This slide shows our system design of hardware and software. First, PPT signals and temperature of the body were obtained by using the MAX 30102 module. Then, the obtained data were sent to our embedded system, whereby the ESP32 microcontroller is used. The data were then processed using an algorithm to extract the 5 vital signs parameters, which are temperature, respiratory rate, SpO2, heart rate, and perfusion index. The 5 extract parameters will then be sent to the NetPi server through the Internet module. At the NetPi server, as we developed an interactive application, this allows users to see 5 vital signs in the form of graphical dashboard.
This slide shows an optical sensor module, MAX-T0102, used to measure PPG signals. The module contains IR and LED, along with their corresponding photodetectors. The MAX-T0102 also has an on-chip temperature sensor. We programmed the ESP32 with the use of a sampling frequency at 33.3 Hz to acquire data from the module, which is enough for the PPG bandwidth. As we mentioned, it is in the range for 0.5 to 4 Hz.
This shows how the MAX 30102 module works. As you can see the diagram inside the MAX 30102, first, the red and infrared LED will emit the light through skin. The oxygenated blood will be absorbed by the red light, and the deoxygenated will be absorbed by the infrared. The remaining light will be reflected to the red and infrared photodiode. The photodiodes will then convert such reflected light into voltage and convert to digital signals with the 18-bit analog to digital converter. The data were then digital filtered and sent to the ESP32 through the I2C protocol. The MAX 30102 also has a semiconductor-based temperature sensor, which can be used to detect body temperature while measuring PPT.
ESP32 is a series of low-cost and low-power system-on-a-chip microcontroller with integrated Wi-Fi and dual-mode Bluetooth. ESP32 is developed from the ESP8266. It's becoming more popular because it can be developed easily. In our project, we use the ESP32 board called VMOS D1R32.
This slide shows our prototype. The ESP32 microcontroller is obtained in the transparent box, whereby the optical sensor, MAX 30102 or the PPG measurement, is attached with a long cable in order to place at an appropriate finger location. Note that this is just a prototype, which can be modified to be in the form of wearable device later.
This slide shows the connection diagram of our hardware. As you can see, the MAX 30102 module is attached to one finger of a subject.
Now let's talk about our software processes implemented inside the ESP32 microcontroller. First, we acquired temperature and raw PPT in the form of red and infrared data from the MAX 30102 module. The raw data were filtered by the low-pass filter. Then, we used our algorithm to extract heart rate, SpO2, perfusion index, and the breath rate. With the Wi-Fi function was activated to transmit 5 vital signs parameter to the NetPi server.
Noise is normally contaminated in low PPG signals caused by ambient light and movement artifacts. Therefore, low PPG signals must be filtered out by a low-pass filter. We use the exponential moving average method to filter noise out. As you can see, the rate or smoothing constant is the main factor which depends on what a sampling rate and cut-off frequency. We use a sampling rate of 33.33 Hz with the cut-off frequency of the low-pass filter at 4 Hz. Then we got the rate of 0.0131, and they can be used in the exponential moving average to filter raw data. This slide shows the two reflected raw PPG signal exposed by the LED and IR wavelength. As you can see in this figure, LED data show higher amplitude compared to the IR amplitude.
This slide shows the PPG signals before and after filtering. We used filtration by low-pass filter, the moving average technique. As you can see, the raw rate data is filtered into the filter rate data, so the data gets smoother. Also for the IR, the raw IR getting smoother by the filtered IR. To obtain the oxygen saturation from rate and infrared PPG, we need to locate the maximum and the minimum amplitude of both rate and infrared to calculate the absorbance ratio. This absorbance ratio represents the ratio between rate absorbed to infrared absorbed by blood. The ratio is used to calculate the SpO2 through a linear equation, which is approximate from the standard R curve equation, so that we can implement this equation to extract SpO2 values in our algorithm.
Let's talk about the calculation of instant heart rate. Instant heart rate is obtained from the time difference between peak 1 or P1 to the consecutive peak or P2, defined as a delta t. The instant heart rate is equal to 60 seconds divided by the delta t, a simple moving average of the current, and the previous heart rate can be used to reduce sudden jump of the heart rate values due to movement artifacts.
From the principle of respiratory sinus arrhythmia, the respiratory rate can be calculated by constructing the pulse rate variability. When the high frequency of heart rate occurs, the PRV amplitudes are small, representing inhalation, while when low frequency of heart rate occurs, the PRV amplitudes are large, representing exhalation. We detrained the PRV signals by taking its derivative to easily detect the min and max peaks of the PRV. The number of these peaks are then used to calculate the respiratory rate by divided by 2.
This slide shows signal processing methods. We implemented 4 main processes. First is a low-pass filter applied to raw PPG signals, whereby a cut-off frequency of 4 Hz is used. Second is a PPG peak locating in which max and min of filtered data are detected. The filter LED and infrared will be used to calculate the perfusion index and SpO2. Third is a calculation of heart rate. And lastly is an estimation of breathing rate.
This is IoT communication between device and NetPi platform. As we explained about MQTT in background, NetPi uses MQTT broker to send and receive data from device. We will start at the control board in NetPi platform. When we click the Start button, NetPi will send the message to broker, and device receive message from the same topic. After that, ESP32 will control the PPG sensor to measure vital sign. If you select time control, NetPi will send the message to control transmission rate in the ESP32. If you click Stop button, NetPi will send the message to the device to stop measuring vital signs.
To connect the internet through Wi-Fi module inside the ESP32 microcontroller, we need to configure security parameters provided in a Wi-Fi library, as shown in this slide, with the service set identifier or SSID, which is the name of your network and its password. We can access through the internet connection.
Now we are going to connect our device to the NetPi server. First, we create a new project name in NetPi Dashboard Designer. Then we got an email from NetPi informing our app ID, key, and secret. According to creating a new project, we put these inform parameter in the ESP32 codes as shown in this figure.
So let's talk about a command for sending data from the ESP32 to the NetPi dashboard. The command is microgear.chat, which we can display both numeric data and historic plots. The values and plots we monitor are the 5 parameters compute for our algorithm. We also indicated the status of operation, which is getting data or pause, whereby the latter appear when pressing stop button on the design dashboard.
On the other hand, when sending commands from the design NetPi dashboard to ESP32, we use the command microgear.publish as a transmission rate is required in this project. We provided a slide bar for adjusting the rate from 2 to 6 seconds per a single acquisition. We also put a start and stop buttons in the dashboard for activating the ESP32 to start and stop acquiring data. Note that the allies for start and stop commands are 2 and 0.
This slide shows our web-based dashboard, which are designed on the NetPi server.
An ability of the NetPi 2015 is that when creating the dashboard on website, it can port to any mobile application platform. Since the NetPi is basically run by the JavaScript, which is compatible with HTML5, as you can see in this slide, the same web-based dashboard appears in mobile application.
Now, let's move on to our experimental protocol conducted with 20 healthy subjects aged between 19 to 22. Our subjects consisted of 10 males and 10 females. This aims to validate the performance of our device for the 4 parameters, which are body temperature, heart rate, SpO2, and respiratory rate. We simultaneously measure body temperature, heart rate, and SpO2 using our device and the standard patient monitoring. The subjects were instructed to breathe associated with the defined metronome rhythm sound on a computer screen. The protocol begins with attaching the vital sign monitoring device to a subject and explaining the steps of the experimental. Next, we monitored their normal temperature, heart rate, and SpO2 for 3 minutes. We then instructed the subject to breathe in and out according to a tick sound generated from the metronome at the rate of 10, 15, and 20 beats per minute. This period took 1 minute. Then the subject was instructed the exercise for 2 minutes, 1 minute for running in the experimental room, and 1 minute for jumping jacks. After that, the subject was monitored for another 3 minutes.
This is another experiment for verifying the data transmission across the IoT-based NetPi server. We conduct the experiments with 8 males and 12 females of age between 19 to 22. We created our own local area network from the 4G mobile network and shared it to ESP32 to connect through the internet. Data sent to the NetPi server were compared to the standard patient monitor with different transmission rates of 2, 3, 4, 5, and 6 seconds. We checked the timestamp in the serial monitor screen each time the data was sent out. The experimental protocol with the IoT communication is the same as the pilot experimental protocol without the IoT communication. but without the validation of respiratory rate.
This slide shows our experimental setup. As you can see, the PPG sensor was worn at the index finger of the subject. This slide shows how to use the IoT-based vital sign monitoring for at-risk patients.
สวัสดีค่ะ วันนี้เราจะมานำเสนอวิธีการใช้งานของอุปกรณ์ตรวจวัดสัญญาณชีพผ่านระบบ IoT สำหรับผู้ป่วยที่ต้องเฝ้าระวังค่ะ มีองค์ประกอบคือ 1. อุปกรณ์วัดสัญญาณชีพที่เป็นปลอกนิ้วดังนี้ค่ะ อุปกรณ์ประมวลผลสัญญาณชีพหรือ microcontroller ESP32 ที่มีการรับสัญญาณอินเทอร์เน็ตได้ การปล่อยสัญญาณอินเทอร์เน็ตด้วย hotspot หรือ Wi-Fi ค่ะ และหน้าจอแสดงผลสัญญาณชีพที่มีการเชื่อมต่ออินเทอร์เน็ตโดยเป็นเน็ตพายบนเว็บเบสหรือว่าบนสมาร์ทโฟนก็ได้ค่ะ ซึ่งเมื่อมีการเชื่อมต่อสัญญาณอินเทอร์เน็ตแล้วไมโครคอนโทรลเลอร์จะมีการแสดงผลเป็นสัญญาณไฟสีฟ้าบนบอร์ดดังนี้ค่ะ วิธีการใช้งานของอุปกรณ์ตรวจวัดสัญญาณชีพในผู้ป่วยที่ต้องเฝ้าระวังผ่านระบบ IoT ขั้นตอนแรกคือการติดตั้งอุปกรณ์โดยสวมอุปกรณ์ไว้ที่นิ้วของผู้ป่วยค่ะ หลังจากนั้นเราจะสามารถกดปุ่ม Start ได้ทั้งบนเน็ตพายเว็บเบสและในสมาร์ทโฟน เช่นนี้ค่ะ การทำงานของเน็ตพายทั้งบนเว็บเบสและสมาร์ทโฟนจะทำงานควบคู่กันไปพร้อมกัน ภายในหน้าจอเว็บเบสของเรานะคะก็จะประกอบไปด้วยปุ่ม Start Stop สำหรับการเริ่มการทำงานและหยุดการทำงานค่ะ และ Getting Data คือสถานะของอุปกรณ์ว่ากำลังรับสัญญาณของอุปกรณ์อยู่ค่ะ Time Control คือการควบคุมความถี่ในการส่งข้อมูล ถ้าหากเลือกการ Control เวลาเป็นมากกว่า2 วินาทีสามารถกดเลือกได้ดังนี้ค่ะเมื่อกดเลือกเป็น3 วินาทีการส่งข้อมูลจาก Serial Monitor มายัง NetPie Web Base และสมาร์ทโฟนจะเปลี่ยนเป็นความถี่เท่ากับ3 วินาทีบนหน้าจอ Web Base และสมาร์ทโฟนจะมีการแสดงผล Heart Rate คือค่านี้ค่ะและบนหน้าจอสมาร์ทโฟนจะเป็นค่านี้ค่ะแล้วก็จะแสดงค่าอัตราการหายใจเมื่อมีการหายใจครบ1 นาทีคือค่านี้ค่ะค่าอุณหภูมิก็คือค่านี้ค่ะเปอร์เซ็นต์ความอิ่มตัวของออกซิเจนในเลือดหรือ SpO2 และ perfusion index ค่ะเมื่อเราทำการกด stop หรือว่าหยุดการใช้งานสถานะของอุปกรณ์จะเปลี่ยนเป็น pause ค่ะเช่นเดียวกันกับบนสมาร์ทโฟนและเน็ตพายจะหยุดการทำงานทันทีค่ะ
Moving on to this slide, which shows an example of our experiment. When a subject was in a rest state, the vital signs of the subject were simultaneously measured using our device and the standard patient monitoring. We print out 5 vital signs parameters to the serial monitor of the Arduino adapter without sending data to the IoT communication. This is the example for the metronome at 20 beats per minute that we used to instruct the subject to breathe at 10 breaths per minute. The subject were assigned to breathe in at first tick and breathe out at the next tick. Like this, as you can see in this animation, the subject were assigned to breathe in, out, in, and then out.
This slide shows when a subject was exercising before coming back to get measured. The exercise was performed for increased heart rate of the subject.
So this slide shows an example of our subject after exercising. As you can see, the subject heart rate is significantly increased.
This slide shows an example of our experiment based on the protocol with IoT data transmission. We conducted the same procedures as the experimental without the IoT, except breathing rate validation. We tested the system with 5 transmission rates from 2 to 6 seconds. As you can see in this computer screen, the 5 vital signs parameters were sent to the NetPy server and displayed on our design dashboard instantly and accurately.
Continue from the last slide. This slide again shows the vital signs results on our design dashboard, which is web-based style on the NetPy server.
This slide shows our serial monitor for the IoT experiment. We observed the vital sign values and timestamps of both the serial monitor screen and our NetPy dashboard. As you can see, we selected a transmission rate of 4 seconds on our NetPy dashboard. And then the ESP32 received a message, incoming message with a number 4 appeared. The ESP32 then updated the timer interrupt to 4 seconds immediately. These experiments were tested with 5 different transmission rates, which are 2, 3, 4, 5, and 6.
To deliberate the accuracy of the device, we calculate the percentage error of each data that we recorded. Such data are heart rate, temperature, SpO2 before exercise and after exercise, and respiratory rate. The data obtained from each subject was average, representing the experimental value, while the average data obtained from the patient monitor represent the actual value. The percentage error of each participant were used to calculate overall mean error with its standard deviation.
This slide shows overall mean errors and their SD of our device obtained for measuring vital signs without the IoT transmissions. We split the results into 2 phases. For the pre-exercise or rest state, the device had an error of 0.51%, while for the phase of after exercise, the error rises to 0.63%. For the SpO2 data, the device can measure SpO2 at fast heart rate more accurate than at slow heart rate. The accuracy of temperature at pre-exercise are more accurate than post-exercise. The accuracy of breathing rate measurement shows approximately the same among the 3 breathing rates, which yields a percentage error around 4 to 5%, with the SD range between 3 to 6%.
This slide shows overall mean error and its SD of our device obtained from measuring vital signs with the IoT transmission. We not only split the results into 2 phases, but also separate the results by transmission rate from 2 to 6 seconds. As you can see in this table, for the pre-exercise, the percentage error of the measured heart rate, SpO2 and temperature for all transmission rates are between 1.16 to 4.07. For the post-exercise, the percentage error of the measured heart rate, SpO2 and temperature for all transmission rates are between 0.52 to 5.93. It is observed that the average error and SD of the exercise state is lower than that of the rest state. Note that the transmission rate of 3 and 4 seconds are the most accurate heart rate data transmission.
This slide shows average timestamp error of different transmission rates obtained from measuring vital signs with the IoT transmission. As you can see in the table, the average timestamp error of both pre-exercise and post-exercise were remarkably close, which is around 1.8 to 1.84%. It is noticed that the transmission rate of 5 seconds gives us the smallest error of timestamp, while the transmission rate of 2 seconds yields the most. This is true since the IoT generally has a small bandwidth. So, if we frequently send data as a heavy load to the server, it will produce a lag in processing and results in delay of transmissions.
This slide shows conclusion of our project. First, the device is able to efficiently measure 5 vital signs per meter, that is, heart rate of not more than 150 beats per minute, respiration rate of not more than 45 breaths per minute, body temperature from 29 to 38 Celsius, the percentage of blood oxygen saturation from 96 to 100%, and perfusion index from 0.01 to 7%. We examine the performance of our device with a normal and high cardiac activity for 4 parameters: heart rate, respiration rate, temperature, and the percentage of blood oxygen saturation. It was found that the heart rate can be measured with an accuracy up to 97.64%. The accuracy of the measured respiratory rate is up to 95%, and the accuracy of the measured temperature is up to 95.41%. The percentage of blood oxygen saturation can be accurately measured up to 98.83%. The vital signs can be transmitted to the NetPi platform with the IoT communication. This device is able to monitor the patient's data on a variety of devices, such as computers, smartphones, and tablets. The device can efficiently adjust the transmission rate from 2 to 6 with acceptable percentage error. In the discussion slide, we observed that our device is more sensitive to changes in heart rate than that from the standard patient monitor screen, Schiller-Argus algorithm. This means that our device is able to detect rapid changes in vital signs, which we'll examine and validate later for this ability. Moreover, the results from experiments without the IoT transmission shows more slightly accurate than that from the experiments with the IoT transmission. Such error could be a delay due to the data transmission process across the IoT and NetPi server. This is also depends on which internet provider that we use and whether the period of use has a peak traffic or not.
In experiment, the device temperature has more value than the patient monitor's temperature because the position of patient monitor's temperature is not in the same position of device. That makes the different value between patient monitor's temperature and device temperature, causing the temperature error to be high, but the error value is still acceptable. So we add PI value in our device because PI is the value indicating the accuracy of the SpO2 measurement. So we put them in the device to make the device more reliable and increase the efficiency of measuring vital signs.
Now, before the end of presentation, we would like to point out some future work. It means that if we have a chance to improve our work, we will conduct it as follows. First, conduct the experiments for checking accuracy of the perfusion index. Next, develop an algorithm to measure blood pressure trend. Then, develop a hardware that's more convenient to use, such as in the form of wearable device. And create an IoT database which can store patients' information and make the user interface that is more friendly for user. Lastly, we will conduct a clinical trial with actual patients. Let's end our presentation with a farewell quote belonging to Nagavara Ramarao Narayana Murthy. The quote is, "Effective use of technology is important to deliver healthcare. By leveraging technology, you can bring down lack of access and cost of healthcare."
Thank you for your attention. I am Navinda Nakrawong.
And I am Namrin Rueang-ngam. Hoping you enjoy our presentation.
Thank you.